So problem 684 in our homework deals with Hess's law. Basically, Hess's law is a fancy way of flipping around reactions until you get the reaction that is required or that you want to calculate the enthalpy of. So here we have three reactions that, as stated, is given in the following data. And we're asked to find the enthalpy of the reaction of this top reaction here. H gas plus Br gas goes to HBr gas. Notice we're asked to calculate the enthalpy under standard state conditions. Standard state is that big O symbol, also called delta H naught. So let's solve this problem here, realizing that this is a Hess's law problem. So I went ahead and recopied the problem, and now let's take the step by step to try to determine sort of a mode of attack. So here's the main problem, here's the main equation that we're asked to find. These are the three equations that we some way, somehow have to manipulate, that we some way or somehow have to change and switch around in order to get this. So the first thing we want to recognize is the H gas is here, but we have two H gases. We have the Br gas here, which is an equation, the second equation here, but unfortunately we have the 2 here. And then HBr is in the product side, so HBr is in the product side here, which is fine. The first thing I'm going to do is, you see here the H gas is in the reactant, but in this reaction, this first reaction, H by itself is in the product. So we're going to flip this reaction. When you flip this reaction, you actually flip the sign. And instead of going for two H's, we actually have one H. So what I'm going to do is actually multiply the first reaction by 1/2 after I flip it. So the scheme here is that we're going to flip reaction 1. I'm going to actually label these 1, 2, and 3, these sort of sub-reactions, and this is the main reaction we need to get via manipulating 1, 2, and 3. So I'm going to flip equation 1 and also multiply it by 1/2. I'm going to do it all in one step here. So remember, we flip the reaction, and this reaction now flips in sign. We multiply by 1/2. That means we multiply this enthalpy standard state by also 1/2. So let's do that. I'm going to do this, I'm going to do this in one step, sort of kill two birds with one stone. All right, and in doing that, this becomes minus 436.4 times 1/2, or same thing as minus 436.4 divided by 2. So the standard enthalpy for this reaction is going to be minus 436.4 divided by 2, or multiplying it by 1/2. It's the same thing, and that value turns out to be minus 218.2 kilojoules per mole. All right, so now the reason why I did that is have my H gas on the reactant side, and here in my net equation I have H gas on the reactant side. Let's do the same thing for equation 2, flipping it and at the same time multiplying it by 1/2. Flipping it changes this to a minus sign. Multiplying it by 1/2 is the same thing as dividing this by 2. So step 2 is flipping reaction 2 and also multiplying it by 1/2. All right, so flipping reaction 2, this is going to be 2Br going to Br2, and then multiplying it by 1/2 gives me Br goes to 1/2 Br2. And like stated before, now by flipping it, this becomes minus 192.5, and also dividing it by 2 or multiplying it by 1/2 will give us, this divided by 2 is minus 96.25. All right, the reason why I did that is now I have my Br gas in the reactant side, which is what I want here. Now let's take a look at this. I have 2 HBr on the product side. I have HBr in the product side here. Before I move on and do anything else, what I'm going to do is I'm going to add these two reactions together. Okay, I'm going to call this reaction A, and we'll call this reaction B. So before we play around with anything with this third reaction here, I'm just going to add A and B together. And remember, when we add A and B together, we add the corresponding delta H values together. All right, adding those two equations, A and B, we add minus 218.2 plus a minus 96.25, and that gives us a value of minus 378.45. Okay, that is the addition of minus 218.2 with minus 96.25. All right, we're going to call this new reaction that we just generated C. So now I've generated reaction C here by adding A and B. So what I'm going to do now is I'm going to add reaction C to number 3, but there's a difference here. Before I add that, I'm going to multiply this by 1/2. So do you see my thought process or thinking in multiplying reaction 3 by 1/2? So multiplying reaction 3 by 1/2, I get 1/2 H2 plus 1/2 Br2 plus 1/2 times 2 is just 1 plus HBr, which is the HBr here. So I'm going to multiply 3 by 1/2. That also means we multiply this by 1/2. And by multiplying it by 1/2 and adding it to part C, we should be able to recapitulate the original equation and get the corresponding enthalpy for the net reaction. All right, so I'm going to multiply equation 3 by 1/2. Multiplying equation 3 by 1/2, like I said before, 1/2 H2 plus 1/2 Br goes to HBr. This gets multiplied by 1/2. All right, multiplying this by 1/2, we got minus 36.2 kilojoules. And now we'll now we'll add this equation to C that we generated here. All right, so here's our reaction that we got from adding A plus B, which was C, which was minus 378.45 kilojoules per mole. Here's the reaction we just generated by manipulating the third equation here. So let's add these two up. You notice that when we add these two up, the half H2 and half H2 cancel. The half Br2 cancel. We are left with H gas plus Br gas goes to HBr. Lo and behold, that is the equation that we're asked to find the delta H of. By the way, this is delta H at standard state. And that equation has a corresponding enthalpy of, well, we'll just add it up here, minus 36.2 plus a minus 378.45, and adding those two, minus 36.2 plus a minus 378.45 gives me minus 414.65 kilojoules per mole. Okay, this is an exothermic reaction. So that is an application of Hess's law, where we manipulated these three equations to get our final equation. Utilizing the individual enthalpies, we got the enthalpy of the entire reaction